The atoms in a solid or a gas tend to repel each other if they're too close, and they tend to attract each other if they're too far apart. This is due to the way the electrostatic charge or the electric charge distributes itself around the molecules, around the nuclei of the atoms making up the molecules. If they get close enough, those electrostatic charges will repel each other, but if they're far away, you tend to get a polarization of charge in the molecules, and we'll talk about that when we get to the electricity part. But that polarization of charge really results in an attraction. Therefore, if we graph the force F between molecules as a function of R, which is a separation between the molecules, we see that inside some distance R sub 0, the molecules will tend to repel each other. Outside of that distance, they tend to attract, but of course as that distance goes off to infinity, the attraction becomes less and less. So there's some point down here at which the maximum attraction occurs, and then it tends to diminish. The potential energy U between the molecules of a substance is going to be proportional to an integral of the force, because potential energy is just an integral of force over distance. Therefore, this potential energy curve is going to be an antiderivative, or going to have the shape of an antiderivative to the F curve. Now, the exact constant of proportionality depends on how many molecules you've got and so forth, but the potential energy of a sample will be an antiderivative of the force function, proportional to an antiderivative. And what's the antiderivative? What's an antiderivative of this force function going to look like? Well, first place, when the force function is 0, the antiderivative function will have a critical point. And in this case, if we look at the rest of the curve, we can see that critical point will be a minimum. We can work that out mathematically. It's not difficult. For positive repulsive force, and really, what we're plotting here is repulsive force, so this doesn't quite look right. When this force is positive, it looks like the potential energy function ought to be increasing until you realize that this is a repulsive force, and really that turns things upside down. So we have really a repulsive force here, and that should be regarded as a negative force, which means your potential energy function will be decreasing. Okay? Until it gets to this point, and now here it looks like you have an attractive force, and that attractive force will then tend to increase the potential energy with a minimum at this point. And this explains a lot about why solids have the volumes they do and so forth. The separation between the molecules tends to go to the 0-point separation, or the natural separation, where we have the lowest potential energy. Just like gravitational objects fall as low as they can go, the potential energy of the whole solid is going to tend to go to the lowest point.